So today we're going to do polynomials again, but more of like an extension of last week. It's going to be more advanced. It's going to include some problems you're probably going to see in the competition. Although the competition is like passed already, next year, AMC 8, AMC 10, AMC 12, whatever. So any math you do is preparation for the future. So we're going to first deal with factoring polynomials, how we generally will factor them, the remainder theorem. We're going to go back to Vieta's formulas. Remember, we had those in quadratics. Today, we're going to extend those. So for quadratics, the Vieta's formulas, there were really only like a specific example of how to use them. Vieta's formulas can apply to all polynomials. So we're going to go and see how that works. And we're going to look at Simon's favorite factoring trick. If you use AOPS, you probably recognize this. It's like a user on AOPS named Simon. He thought up of this factoring trick, and it is very, very useful. So first of all, if you want to factor a polynomial, so let's say we have this polynomial. This looks a little complex, but it's basically just saying that this is the first coefficient, this is the power, the second coefficient, the next power. See that it's one less, and then we go all the way to the end. So that's just how we're going to generally write a polynomial. So if we want to factor this polynomial, all the rational roots can be stated in the form fn over f1, where fn are the factors of a of n, and f1 are the factors of a of 1. Okay, so rational roots, this method allows us to find the rational roots. What does rational mean? Someone turn on their mic and tell me, what is a rational number? Is 1 a rational number? Yes or no? Someone can unmute and tell me, is 1 a rational number? Come on, guys. It should be pretty simple. Is 1 a rational number?
Yeah.
Yeah. So a rational number is a number that can be represented as a fraction. Okay, as a fraction. So if we have 1/2, that works. Square root 2 is not rational. No. Square root 2 is not a rational number. Pi is not a rational number because those can't be represented as fractions. Okay. You can see why that makes sense because rational, it has the word ratio inside. If you can represent a number as a ratio, then it's rational. And fractions are ratios, as we know. So the simple here tells us, can we write out the possible rational roots of 2x to the 7 minus 15? So this method gives us all the possible rational roots that could exist. So the formula tells us that all the rational roots are in this form, f of n over f of 1. So all the factors of negative 15 over all the factors of 2. So let's write out first all the possible factors of negative 15. All right, we can have 15, 5, 3, or 1, right? And I don't really care about negatives here. So what we can actually do is we can figure out all the possible factors of 15, all the possible factors of 2, which are 2 and 1. I like to write them this way. And then we pair them together. We just pair them together. Let's start pairing this. 15 over 2, that's 1. We actually take plus or minus here because negative factors exist, right? We can have negative 1 as a factor, negative 3, negative 5. And if we did negative 15 over 2, that would give us negative 15 over 2 as a factor. All right. I'm not writing all those possibilities out. It's just a reminder that the negative numbers can be factors, which means you just find the fraction and take the plus minus in the end. Okay, so all you really need to do is write out the positive factors and then take plus minus. Next pairing, 5 over 2. 3 over 2, plus minus 1/2. Okay, so those are 4 of the possible factors. So now we're going to take these. So we got 15, plus minus 15, plus minus 5, plus minus 3, plus minus 1. So we have 8 possible rational roots, and those are the only 8. So how do we determine if it's actually a root or not? We have to plug it in and use synthetic division. So yeah, so at that point, it gets pretty complicated. We can write out the possible rational roots. Those are the possible ones. But then we need to just manually check if it works or not. Okay, so when you find one that works, you can divide it and factor it and get a smaller polynomial and then factor it again by trying other numbers. Any questions here? So basically, we take all the factors of the last term, all the factors of the first term, and we pair them together, dividing, and take the plus minus of those because we can have negative factors. Okay, so in this case, we had 8. No, not 8, 16 because we have plus minuses. All right. Let's factor this polynomial. It's often easier to factor something with a leading coefficient of 1 because you won't really get any nasty fractions. So I'll give you 5 minutes for that one. Okay, so as we come back here, so first of all, we have to figure out what are the possible rational roots. So we're going to write out all the factors of 10, all the factors of 1. So we got 10, 5, 2, and 1 just as a factor of 1, right? So let's pair all these together. So first we have plus minus 10 over 1, plus minus 5 over 1, plus minus 2 over 1, and plus minus 1. Since we're doing it over 1, it doesn't really do anything because when we divide by 1, number stays the same. So those are our possible rational roots. So now it's time to just test those out and see which ones work. The easiest one to test out by far is 1, right? So you can see we have regular old 1 in here. Let's just test it out. It's the easiest one. So let's test out if 1 works. We're going to use some synthetic division here. Remember, we put 1 inside the little box. So if 1 is a factor, we should get 0 at the end. We should get 0 as a remainder, which means it's a factor, right? So let's test out 1. Does it work? Oh, yes, it does. Hooray, 1 works, which means x minus 1 is a factor. So we know that x minus 1 is a factor. We got pretty lucky there because 1 worked. If it didn't work, we would have to try out the other ones. So as you can see now, our next polynomial is x squared plus 3x minus 10. No remainder, which means that was because x minus 1 was a factor. Okay. Well, since we have a quadratic, we can just factor it regularly like a quadratic. Of course, you can still use your rational roots and test out which ones work. But since it's already a quadratic, we can just factor it normally like a quadratic does. So this is x squared. This is x plus 5, x minus 2. Factoring. So these go in there. So the factored form is that. Right? Any questions? Cool. I'm going to the remainder theorem. This is a kind of shortcut. If the remainder to f of x over x minus a for some number a is r, then f of a is r. Okay. So basically what this says is that if we want to find the remainder of a polynomial divided by some binomial, x minus a, then if we plug in a into the polynomial, we should get the remainder. Okay, so let's just give an example here. Let's take the polynomial x cubed minus 2x squared plus 4x minus 4. Okay, how do we figure out what the remainder if this is divided by x minus 1? Do that. So in this case, there are 2 ways we can find the remainder. Of course, we can always use synthetic division and see what we get. So let's do that. So it looks like the remainder is -1. We can also find the remainder by plugging 1 into the polynomial. Plugging 1 into there. So we get 1 minus 2 times 1 plus 4 times 1 minus 4. This is also the remainder. As we can see here, we also get -1. Okay, so 2 ways we can find the remainder. If we have like a binomial there, we can either use synthetic division, or we can literally just plug it in, plug the a value in and into the polynomial, and that will give us the remainder. I think it's pretty cool. Any questions here? Cool. So let's go on. Quick, this should take, if you're speedy at math, this should take 2 minutes maximum. So after 2 minutes, I will call on a random person and they will have to give me their answer. So quick, is x minus 1 a factor of these 3 polynomials? You have to give yes or no to either of them. So remember, if it's a factor, then the remainder turns out to be 0. Okay. All right, first kid. So any volunteers first? Any volunteers for the first one? Jenny, what do you think?
Yes.
Yep, it is, because 1 minus 3 plus 3 minus 1 is 0. Good. So, any other volunteers for the second one? Chloe.
No.
Good. Because you can see we have 1 plus 9 minus 8. That's 2. Okay, so no. The last one. Jonathan, the last one?
No.
That is correct. As you can see here, that was this one is mainly one about patterns. We compare these together. These cancel out, right? 1 minus 1 gets to 0. These cancel out 0. If you can see, every pair starts with a positive and ends with a negative, which means this negative right here was the end of a pair, right? Which means this guy was 0. So all the rest are 0. We can ignore those. We have a 1 at the end. It's not 0. So the sum was 1, which means, nope, it's not a factor of 1. Okay, very good, guys. So as you can see here, what we literally did was we added the coefficients, right? Because when we plugged in -1 there, when we plugged in 1, we just got 1. So what we literally did was adding the coefficients, which is quite a useful tool you might want to use when you're dealing with, so whenever you plug in 1 into a polynomial, you're literally just adding the coefficients, okay? So some problems are going to say, what is the sum of the coefficients of this polynomial? So you know what to do. You would just plug in 1 in there, and that would give you the sum of the coefficients. As we saw, that's what really happened when we were doing this problem. So now let's do a more in-depth one. So using the remainder theorem, what is the remainder? And verify that with synthetic division. 3 minutes for this one. All right, so with the remainder theorem, all we need to do is plug in 1 in there. As we can see, if we plug in 1, all we're really doing is adding the coefficients, right? So the coefficients are 1. So we're basically going to do 1 plus 9 minus 4 plus 3 minus, plus 4 minus 1. Was that a minus 9? Oh, yeah, it was a minus 9. Negative 1 plus 1 does go out to 0. 1 minus 9 plus 4 plus 3, that is negative 1. So the remainder is negative 1. Let's verify this with synthetic division. So we got 1 minus 9, 4, 3, negative 1. And be careful here, there is no like ax term. There's no x term with a coefficient of 1, with a power of 1. So what we need to do is actually put a 0 there. Be very careful here. So that's the actual way to do it. Plug in 1, 1, negative 8, negative 8, negative 4, negative 4, negative 1, negative 1, negative 2, negative 2, negative 2, negative 2, negative 1. Ah, we have the same remainder. So just revealing that remainder term does work. So whenever you have like a really complex polynomial like this, it's better to just use the remainder theorem if the numbers are not too big. Okay, now I can move on to Vieta's formulas. So if you recall when we were doing quadratics a while ago, if we had like ax squared plus bx plus c, we knew the sum of the roots. So r1 plus r2, the sum of the two roots we have, those must be equal to negative b over a. If we have the product of those, we get c over a. Does everyone remember those? Yeah, so those are Vieta's formulas for a quadratic. We can actually have Vieta's formulas for any polynomial. So the way it works is that let's say we had, I'm going to write the polynomial in this general form again. So f of x will equal to first coefficient times the first power, second coefficient times the next power, so on until we have the last constant. Okay, this is the general form we can write a polynomial in. The sum of the roots. So however many roots this has, the sum of these roots is equal to negative a2 over a1, always. So first, we take the second coefficient, we divide it by the first coefficient. That's what we did with the quadratics here. We had the sum, we did the negative of the second coefficient over the first coefficient, right? So the quadratics is just kind of like a specific example of this general formula. So the sum is literally just the second coefficient over the first coefficient. You take the negative of that. The next one is if we pair the roots together in multiples. So r1, r2. So multiplying those r1 times r2. If we pair them together, r1, r3 plus r1, r4. We can also have plus r2, r3. So all the combinations of pairing these roots together and multiplying them, and then we add all of those together. This lot equals a3 over a1, positive a3 over a1. Okay, as you can see here with the quadratics, we only had two roots. If we pair them together, that was equal to positive c over a, the third coefficient over the first. If we were to pair them in thirds, this is where the quadratic stops working. If we were to pair them in thirds, three groups of 3. So r1, r2, r3 plus r1, r2, r4. We also have like r1, r3, r4. So all the possible pairings of groups of 3 together, and we add them all together, this what we get is negative a4 over a1. The next coefficient over the first coefficient, take the negative of that. If we were to put them in 4 groups of 4, so on, add them all together, you would get positive A5 over A1. And this pattern continues. So as you can see, if we pair them in groups of 1 and add them together, we take the negative of the second over the first. If we pair them in 2s and we add them together, it's the positive of the third coefficient over the first, fourth over the first, fifth over the first. And you can see we're oscillating between negative and positive here. As you can see here, the first fraction we had to take, we didn't just have to take the ratio between the second coefficient and the first coefficient. We had to take the negative of that fraction. The next fraction, it's actually positive. We don't need to take the negative. The next one, we do need to take the negative. Next one, we don't. So the next one, as you can predict, we should have the sum of all pairings of 5 together, R2, R3, R4, R5, etc. This must equal to the negative of A of 6 over A of 1. So these are the sixth coefficient over the first coefficient. So that's how the pattern goes. We start out, the first one is the negative. The first one is negative. And then we oscillate between positive and negative from then on. Okay, so this is the general form. We can keep going. We can keep going forever. For however many roots this polynomial might have. So that's the more general form of Vieta's formulas. Any questions here? It's a lot to process. So in the end, let's say this polynomial had eight roots. Then there would be only one way to pair 8 of them together, right? So the product of all the roots then, this must equal to A of 9 over A of 1. How did I know that? Well, you can see if we pair them in groups of 1, we had the second coefficient. Groups of 2, we had to have the third coefficient. Groups of 3, we had to have the 4. So groups of 8, we have to have the 9 coefficient. Okay, over the first coefficient. And do we take the negative or not? Well, the first one was a negative, and that had an even like sub number here, A of 2. So whenever we had the second coefficient, that's an even number, we had to take the negative. The third coefficient, that was odd. We didn't need to take the negative. Here we had 4, we had to take the negative. 5, no. 6, yes. So 9 is an odd number. We don't need to take the negative. So that pattern goes on. So all the even numbers here, A of 4, A of 6, A of 2, those have to have a negative attached because it went in that order, right? So if we want to find the product of all the roots, that's literally the last coefficient over the first coefficient. Okay? Because A of 9 would be the last coefficient because you can see here, we kind of go like, so let's say this, if a polynomial has 8 roots, as in this example, the leading coefficient would be 8, right? Then we have some term with x7 all the way down to x0, which is the constant term, right? This was the A of 1, this was the A of 2. If you keep going, this would be A of 9. Okay, so if you want to find the product, so generally, if you want to find the product of all the roots, it's the last coefficient over the first coefficient, and you might have to take the negative depending on how the pattern works out. Okay? So some problems here. Find the sum and product of the roots of these 3 polynomials. I'll give you guys 5 minutes and I'll call on you. I'll first take volunteers and then I'll call if there are calling people if there's no volunteers. All right, so first, let me take volunteers. For the first one, what is the sum and product of the roots? Any volunteers? Jonathan?
The sum is 7 and the product is 3.
Good. Yeah, so let's go over how Jonathan got that. The sum, remember, is the negative of the second coefficient over the first one. The first ratio is negative. Got to take the negative of that. So it was negative 7 over 1. Negative 7 over 1. So this would equal to 7. This was the sum. Nice job. So the product would be the last coefficient over the first coefficient. We don't know if we have to take the negative or positive yet. So let's figure out which one we should use. So for this one, we had to take the negative. So let's label that with a minus sign. That means whatever coefficient times x4, that would be positive. That would mean whatever coefficient times x third, that we have to take the negative of that ratio. And this goes on. You can see that since this is x to the 0, we can consider that as the constant term x to the 0 power. All the even coefficients, all the ratios corresponding to those, we don't need to take the negative, right? Because x to the 4th, that would be a positive. If we were to keep going, x squared would be a positive, x1 would be a negative, x0 would be a positive. So this basically tells us, do we need to take the negative or not? We don't. Great job. So the next one, any other volunteers? What is the sum and product of that one? I think this one should be the easiest one by far. Any other volunteers? Okay, I'll call on someone then. How about Richard? Any idea about the sum or product of the roots? Richard?
Honestly, I don't know.
Okay, so what was the part that you kind of got stuck on here? Do you remember the Vieta's formulas from the last slide?
Yeah, it was, one of the formulas was R1 plus R2 equals BA divided
That was for a
R.
quadratic.
What?
That was for a quadratic, right? That was what we kind of did last semester.
No, I don't know.
Okay, well, Jenny has her hand raised. Jenny, do you know?
The sum is negative 1.5 and the product would be 0.5.
Yep, the product would be 0. The sum is negative 3/2. Correct. Because the sum, as always, is the negative of the ratio between the second and the first coefficients. The ratio is 6 over 4. The sum would then be, we have to take the negative of that. So negative 3/2. The product is the last coefficient over the first coefficient. The last coefficient is actually 0 here. Okay, so I'm basically talking about the constant term. The last coefficient basically means the constant term. So if the constant term is 0, then the product would be 0 over 4 plus minus, I don't know. But anything, if it has 0 in there, it's got to be 0. So product is always 0. And you can easily see why that makes sense, because if we factor an x out of that, we can literally factor an x. 4x squared plus 6x plus 2. We know that x equals 0 must be one of the roots. So any product with x equals 0, it goes to 0. Okay, the last one. Any volunteers for that one? Okay, Adrian. Do you have any idea of what the sum or product is? Adrian? Okay, I don't think he's there. So Wesley. Wesley? So the last one, sum and product. Oh God, I think he's not there either. So I'll just do this one. So the sum, oh, Jonathan, do you have your answer for this one?
Yeah, the sum is 0 and the product is 8/3. Yeah.
Perfect. Perfect. So how Jonathan did that was the second coefficient over the first coefficient. There is no second coefficient. It's 0. So the sum must be 0. The product is the last one over the first one. -8/3. Is it a positive or a negative? We got to figure it out. Do we have to attach a negative or positive to that? Well, if we had an x, this line represents x to the 100. If we had a coefficient there, we'd have a negative for that. And then we had something x to 99. If we had a coefficient, that would be a positive. Make x to 98, negative. So the pattern seems like we have to take the negative if we have an even power. This is also an even power, remember, the constant term is x to the 0. So that is an even power, you got to take negative. The product is indeed 8/3. Very good job, Jonathan. All right. So, quickly go over these two problems. Doesn't seem like we have time for Simon's favorite factoring trick, so we will just cover that next week. Okay. Okay, so for the first one, what we gotta do is the trick here is to actually expand that product out. So if we expand out a plus 1, b plus 1, c plus 1, let's do that real quick. Okay, so let's expand that. I'm going to first multiply these two, ab plus a plus b plus 1. If we multiply these two together, what we should get is abc plus ab plus ac plus bc plus a plus b plus c plus 1. So now we can use Vieta's formulas. If you can see here, ABC, that's the product of the roots. So let me label these with a minus and a plus and a minus, just to remind us how we're going to multiply, if we need to multiply the ratios by a negative or not. Okay, so the first one was always a negative, the second one was a positive, the last one would then be a negative. The product is just negative 15 over 1 then. This is A, B, C. Now we also know that if we pair each two together, those pairings of 2, that's the third coefficient over the first coefficient, right? Because this one was pairings of 1. And the next one will be pairings of 2. So this is actually the third coefficient over the first coefficient. As we can see, we don't need to take the negative of that. So that would just be 9 over 1 equals 9. And that's AB plus AC plus BC. Sum of the roots, that we have to take the negative of that. So it's negative 4 over 1, which is 4. And that's A plus B plus C. As you can see here, we have our sum basically. This is 15, this is 9, this is 4, and this is 1. So our sum is just 15 plus 9 plus 4 plus 1. What we get is, quick maths here, 30, oh my god, what is wrong with my brain? 30, no, not 30, 29. Oh my god, that took too long. So 29, that is the F value, okay? That's one really cool application of Vieta's formulas. Second one, I'll go over this one real quick. There are 3 ways to find the answer. We can just multiply it out because the polynomial is literally just x minus 3, x plus 4, and x plus 2. Multiply it out, find the coefficients, and add them together. The second way is we can evaluate each of the coefficients independently using Vieta's formulas. Because this will be in the form ax third plus bx squared plus cx plus d. That would be the form of the polynomial. A is 1, so we can get rid of that. B, we know that negative b over 1 must be the sum. So negative b over 1 would be negative 3. Positive c over 1 would then be if we pair them together and we add them together. And you can see that if we do that, we can find each of the coefficients independently and then add them together with Vieta's formulas. The last way is the tricky way. It's the easiest way. Remember when we talked about how if we want to find the sum of the coefficients, all we really need to do is plug in 1 into that polynomial, and that will give us the sum of the coefficients, right? So we know that f of x is x minus 3, x plus 4, x plus 2, right? So if this was in expanded form, we would have ax third plus bx. If we plugged in 1 here, f of 1, all these would go away. All we have left is the sum of the coefficients, right? A plus b plus c plus 1. So all we really need to do is plug in 1 here. So replace these x's with 1s. We don't even need to expand it. And this will give us the sum of the coefficients. 1 minus 3 is negative 2. This is negative 2 times 5 times 3, negative 30. That's the easiest way. So whenever you want to find the sum of the coefficients of any polynomial, plug in 1 in there, and that will give you the answer. Okay, so that's one extra little tip and trick that you can use. All right, so for whoever that volunteered today, thank you so much for participating. And I'll see you next week then. Bye, guys.
Bye.
Bye.